Hi everybody. Say we're going to look at section 5.2b, and we're dealing in this one with the natural logarithmic function. I'll try to keep it moving. You'll notice there's another video in this same section that deals with graphing. That's not my video, but Patrick JMT does a really nice job. So if you want to get a little more help graphing logarithmic functions, make sure you watch his video as well. Alright, let's take a look at this. We see that f of x is equal to e to the x is 1 to 1. If you think about that graph, we've already seen it before. It looks roughly about like this. It's going up. That's not a great graph, but it's 1 to 1. It's always increasing. It has an inverse function. The inverse of that is called the natural logarithmic function, okay, and is denoted by the special symbol lnx. It's actually French for logarithme naturel, which we just read ln x, or we read it as the natural log of x. Note that the natural log is written without a base, just like we did log, of 27 is equal to log base 10 of 27. We just don't write it in there. Same thing with the natural log of x. I could write this as log base e of x, as you see down here, but we always write it as ln x. Why? Efficiently lazy. It's right. We only need 3 symbols here, where over here we've got 5. It's much quicker. Everybody kind of knows once you've seen it. ln x means that. Just make sure you recognize that. I usually make my L with a little cursive L, so I know it's that and not one N. Okay. Also, we know the domain x has to be greater than 0. So here's the actual definition of the natural logarithmic function. Let's move on. All right, here you see e to the x graphed nicely here, better than my slop on the last one. G of x is equal to ln x, and here is its inverse. You can see it's certainly reflected over the line y equals x that you would see right here. Most calculators, when you look this up, it's got an ln button. If you look at a TI-80, any of the graphing calculators, it has its own button. All right. So let's use that a little bit. Let's go ahead and calculate these values. I want you to pause the video at this point in time, and I want you to, well, not yet, but go ahead and calculate each 4 of these values, find out what they are, pause the video, calculate the values, and then check to see your work. I'll put the answers up in just a sec. So go ahead and pause it at this time. Alright, here are the answers. You should, to 4 decimal place accuracy, the natural log of 2 is equal to 0.6931. And it's oftentimes we go to 4 decimal place accuracy. Natural log of 0.3 is equal to negative 1.2, let's try that again, negative 1.204. And you'll notice some rounding happened there. Here I got the natural log of negative 1, but if you recall, that is a value that's less than 0. That is undefined or does not exist. So we can't do that one. And finally, the natural log of 1 plus the square root of 2 is equal to 0.8814. All right. Hopefully you did real well there. Check on your work on that. Let's move on. Some properties that we have. The natural log of 1 is equal to 0 because e to the 0 is 1. And you might say, where did this e come from? But remember, I really have this as log base e of 1 is the same as the natural log of 1. Right? That's just a shortcut way to write all of that out. Log base e of 1 really means, I'm going to have, let's say that's equal to x, right? That means my base, e to the x power, which I don't know what it is right now, is equal to 1. Well, the only way that works is if x is 0. And so that's why we get natural log of 1 is equal to 0. In a similar vein, we can look at this natural log of e is equal to 1. That's even more obvious if you write it this way. Maybe you want to try that out to convince yourself that's true. Because these are inverses of each other, in property 3, the natural log of e to the x is equal to x, and e to the natural log of x is x. Because of the inverse properties, that one's really nice. We love using these two properties right here. And finally, the one-to-one property, we saw this with a common log. It says if I take the natural log of x is equal to the natural log of y, since they're one-to-one functions, the only way that's true is if x equals y. And I could throw an example down here. You know, if I said the natural log of 3x plus 5 is equal to the natural log of, I don't know, I'll just make something up, x minus 6. Oh, that might not work very well. How about x plus 14? Probably a terrible example. But the only way this is going to be true is if these two equal each other. So I'm going to say 3x plus 5 is equal to x plus 14. Solving here, I'm going to take, subtracting 1x, I get 2x. Subtracting 5, I get 9. And we see that x is equal to 9/2. Go ahead and substitute those values, that value in on both sides to make sure both of them are defined. And I think you see they will. So pretty straightforward. Finally, let's take a look at this human memory model. And so what we're taking a look, kind of combining some things with psychology here. Just don't tell Mrs. Carlson we're doing that. But if they're in a psych experiment and they're really asked to see how much they actually recall of that material. That's what this talks about here. The average scores for the group are given by a human memory model, which is f of t is equal to 75 minus 6 times the natural log of the quantity t plus 1. And we're looking at 0 is less than or equal to t is less than or equal to 12, where t is the time in months. So basically we're saying how much do you remember over the course of a year? So this again is done by a regression model, this time a logarithmic regression model, rather than the linear ones that we've maybe looked at earlier. So as we scroll down, let's take a peek. What was the average score on the original, that is when t is equal to 0, exam? Well, we can work that out right here, and you'll notice that if I put that in, I got 75. So this is really f of 0, right? Is equal to 75 minus 6 times the natural log of, and t this time is 0, so it's just natural log of 1. Well, what's the natural log of 1? If I go back a few slides, if you go back, you'll see the natural log of 1 is 0, so this answer is simply 75. I'd like you to go through and compute the next two down here. Pause the video, figure it out, and then I will write the solutions to those in a second, and then we'll go on to the next page. So here are those answers. F of 2 is equal to 75 minus 6 times the natural log of 2 plus 1, which is 3, which I got to be 68.408. 68.408. And f of 3, I won't write all the steps out. Excuse me, f of 6 we're looking at. That's supposed to be a 6. Is equal to, I got that to be 63.325. So you can see there's some degradation in what they actually remember. Over time, right? Now, could we graph this information? Well, of course the answer is yeah, we can. So let's go ahead and take a peek. These numbers right here we'll use on the next slide. So when it was 0, it was 75. At 2, it was 68.4. I'm just getting to the nearest tenth because that's something we could do. At 6, it was 63.3. And so if I were to graph these 3 points, here's going by 10, so at 0 it's 75. Maybe I'll use a different color so you can see it a little better. How about purple? Okay. So I do that one right here. When at 2, it's 68.4. So that's about right here, I think. At 6, it was 63.325. 63. So this is kind of a strange looking curve. Maybe we should consider 12. So let's look what that's equal to at 12. I get 59.6, I think. It's 59.6. So that curve looks, well, that's really close up there, isn't it? This curve generally then has this look, ooh, not like that. About like this, right? Not the most interesting curve in the world, but if you notice, at some point in time it appears that they're still losing some information, but they're retaining quite a bit over time. You may want to do this on your calculator or go to desmos.com and do the graphing there. You'll have a better sense of it, and you can set your window up just like we did. If you want to see more of that curve, you might do a skip here and say instead of going by tens on the way up, we might skip up to, let's say, 50 here, and this might still be 70. You'd be able to see a little bit more pronounced how much the graph is going to look like. All right, hopefully this is helpful for you. Go ahead and get to work on the homework. Be good to your sub today, and thanks for watching. Have a good day.